All right, so in this section, we're going to establish some basic differentiation formulas that will be kind of reusable tools, rather than finding the derivative of every single function like one by one. And the first one is going to be the derivative of a constant. So I'll state it as a theorem. The derivative of a constant function, that's d over dx, of just some constant c is equal to 0. And to establish that, let's just look at a simple proof. Let's define the limit as h goes to 0 of f of x plus h minus f of x all over h. But since the f of x plus h, it's a constant function, so it's always c, right? So this is the limit as h goes to 0 of c minus c over h. This is the limit as h goes to 0 of just 0 over h. And since that 0 over h for any constant h is always 0, as long as h isn't a 0, right? For any value h, it's 0. And the limit is the value of this as h approaches 0, but not when h equals 0. It's going to be 0. So now the derivative of a linear function, that's just the function f of x equals x, that derivative is equal to 1. And as a proof, we can establish this pretty easily. Let's take the limit as h approaches 0 of f of x, which x plus h, right, which is just x plus h minus x over h. And this similarly is actually pretty simple. That's the limit as h goes to 0 of, well, it's just h over h, which is just 1. So this is going to be 1, right? H over h is 1. Okay, so we have the derivative of a linear function and a constant function, and let's try to generalize with the power function. All right, this is called the power rule. It says for any positive integer, an n, that the derivative of x to the power n is n times x to the power n minus 1. And let's see how this can be proved. So for the proof, we'd take the limit as h goes to 0 of this binomial x plus h to the power n minus x to the n all over h. Hope my n's and h's don't look too similar to each other. Try to make that a little bit more n-like. All right, so we're going to have to expand out this using the binomial theorem. And you'd have to maybe look that up. Really, we don't have to look up the whole binomial theorem. We just need the first couple of terms. The first term, if we expand it, would be x to the n. And then we're going to be plus, we'll have, let's see, what do we have? We have n times h x to the n minus 1, and then we have a whole bunch of terms that have h's until we finally get to an h to the power n minus x to the n over h. Now this is the expanded out binomial with a whole bunch of stuff in between that I didn't write because it's not really going to matter. Any term that has h to a power higher than 1 is going to go to 0 when I cancel things out. So the main thing is to notice I have x to the power n and I have minus x to the n. So those actually subtract, those give me 0. And then after that, the only term that where the h cancels is going to be my term, this term here. Every other term has x to a power that's higher than 2. So you can factor out an h and you still have, you have h to a power higher than 2. So you're going to still have a bunch of h's there. And so this is going to be the limit as h goes to 0 of, let's see what we have. First we have h times n x to the n minus 1 over h, and then I'm going to add the other stuff. It's going to be, so this next one is going to be, well, it's h squared times some stuff, right? Let me be a little more specific. We have x to the n minus 2 times h squared, and then we have some coefficient. Then we have x to the n minus 3 and h to the third, and then we have some coefficient, and then all the way down to h to the power n. All of that over h. This is what my point I'm trying to make. All of those terms, the power of h is greater than 2. So even after you cancel the h, all of the numerator is just going to go to 0. And those h's cancel, so what we get is this n times x to the n minus 1. So here's a few examples. Let's find some derivatives. Let's find the derivative first of f of x equals x to the 6th. Well, f prime of x says it should be 6 times x to the 6 minus 1, which is 6x to the 5th. That's the power rule in action. Let's take y equals t to the 4th and just evaluate that. Well, y prime is going to be 4t to the 4 minus 1, which is going to be 4t to the 3rd. And if we have y equals x to the 1000th power, well, y prime is going to be 1000 times x to the 1000 minus 1, which that's 1000 x to the 999th power. So there's the power rule. It's not too bad. And actually, you can see that if f of x equals, let's just x, you actually have f prime of x following the power rule, right? So it would be, so this is like x to the first power. That'd be 1 x to the 0th power. And what's x to the 0th power? That is 1. So it's just 1. So that actually follows the power rule as well. In fact, we can generalize the power rule for any real number exponent. So the general power rule is given here, and it actually turns out that this is true for not just positive integers, but actually for any real number exponent that the power rule applies. I'm not going to do the proof here, but you should know that this power rule works for any x to the n, no matter whether n is a fraction or negative or a square root of 7 or whatever it is. The power rule works for any real number exponent. For example, if we had f of x equals 1 over x squared, we can actually write that using an exponent, which would be x to the minus 2, right? And so f prime of x would be, well, it's minus 2 x to the minus 2 minus 1. So it's going to be minus 2 x to the minus 3, which we could also write as minus 2 over x to the 3rd. So that's the power rule for a negative exponent. Here's another example. So if y is cubed root of x squared, which we can write as a fractional exponent, that's x to the 2/3. Well, y prime is going to be 2/3, that looks like a 5, 2/3 x to the 2/3 minus 1, which, let's work that out, 2/3 x to the, that's 2/3 minus 3/3, right? That's going to be minus 1/3. That's 2/3 x to the minus 1/3. What is that? That's the cubed root. That's 1 over the cubed root of x. Yeah, so there you go. I mean, you could multiply the numerator, and so you'd have 2 over 3 cubed root 3. But anyway, that's fine. So here's another example. If I wanted to find the equations of both the tangent line and the normal line to the curve y equals x root x at the point 1, 1, here's how we do it. Now the normal line is perpendicular to the tangent line. So the tangent line and the normal line meet at a 90-degree angle at that point. Okay, but let's find out what we need to do. Well, first let's write y is, instead of x root x, it's x times x to the 1/2. And so this is x to the 3/2. Okay, so that means let's find the derivative, y prime, that's 3/2 x to the 3/2 minus 1. Well, minus 2/2, let's write. Minus 2/2. That's the 1/2 again. But if we wanted to evaluate it, let's evaluate y prime at x equals 1. Well, it's going to be 3/2 times 1 to the 1/2, which is just 1. So this is 3/2. So at this point, the slope is 3/2. So if we want to do point slope form, the tangent line, right, we do y minus 1 equals 3/2 times x minus 1. That's how we would write the tangent line. The normal line, the slope is going to be the negative reciprocal, i.e. it's going to be -2/3. And so the normal line is going to be y minus 1 equals -2/3. And here's a sketch of the function as well as the, you can see the tangent line and the normal line equations as I put them in, and they both do meet indeed at the point 1, 1. You can see how they meet at a 90-degree angle, where the tangent line it brushes up against the curve and then it goes off, and the normal line is meeting the curve at a 90-degree angle. All right. All right, another theorem that we can use, the constant multiple rule. If you have a constant times a function, a constant times a differentiable function, the derivative of c times f of x will be c times the derivative of f of x. So you can kind of pull that constant scalar out. And the proof is going to come from the facts about limits, actually. So the derivative would be the limit as x approaches 0 of c times f of x plus h minus c times f of x over h. And because of the limit rules, we can actually pull the constant out of this. We're writing the limit, the c first, and then this limit. So this is just c times f prime of x. That's all. You don't have to do any actual derivative to prove this is true. It just has to do with the fact that you can factor out the constant with limits. Yeah. For example, if we want to find the derivative of 3x to the 4th, well, this is 3 times d over dx of x to the 4th. Okay, and we already know the power rule. That's 3 times 4x to the 3rd. So this would be 12x to the 3rd. There you go. That's how we find the derivative of this, using this constant scalar rule. Now we can actually handle all of the terms of a polynomial. But in order to handle like a full-on polynomial, we need to know something else, and that's this. This theorem is called the sum rule. Now, if you have two differentiable functions f and g, then the derivative of f plus g is going to be the sum of their derivatives. And this again is going to follow from limit rules. So the derivative of f of x plus g of x would be the limit as h approaches 0 of f of x plus h plus g of x plus h, all of that, minus f of x plus g of x. So you can see all of that over h, as I said, as h goes to 0. By facts about limits, though, this can be separated out as two limits, f of x plus h minus f of x over h as h goes to 0, plus the limit as h goes to 0 of g of x plus h minus g of x over h, which is simply f prime of x plus g prime of x. So this is just something that we can prove using facts about limits that we've already worked with. All right, now we have a theorem called the difference rule, which is kind of like the same thing. As long as you have two differentiable functions, f and g, the derivative of their difference is the difference of their derivatives. And this is going to be, since we already established the constant scalar rule, you have to just note that f of x minus g of x is just f of x plus -1 times g of x, right? And so the derivative of that, of f of x plus -1 times g of x, is the derivative of f of x plus the derivative of -1 times g of x. This is just from the addition rule. And by the constant scalar rule, we can take the minus 1 out, and we can write d over dx times g of x. And we know that that's exactly the same thing as just minus d over dx g of x. So this is just f prime of x minus g prime of x. And so that's the proof of this. It comes, as I said, from the addition rule and the constant scalar rule, or constant multiple rule, I should say. So let's take this example. Let's find the derivative of x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x to the 3rd minus 6x plus 5. So the derivative, let's just call this y. Okay, so y prime. Let's do it part by part. First, the x to the 8. We're going to have 8x to the 7th. Okay? Then 12x to the 5th, it's going to be 12 times 5x to the 4th. All right, then the next one, 4x to the 4th minus 4x to the 4th, we'll have the minus 4 times 4x to the 3rd. And then the 10x to the 3rd, well, I'm going to write 10, and then 3x squared. And then minus 6x, well, the derivative of minus 6x will be minus 6 because it's linear. The derivative of 5 is 0 because it's constant. So I can clean this up just a tad. 8x to the 7th plus 60x to the 4th minus 16x to the 3rd plus 30x squared minus 6. So we found the derivative of a polynomial. And now you can see all polynomials are going to be basically like that. If you want to find the derivative, you just do the power rule and the constant scalar rule one by one, and you got it. Here's an example. Let's find the points on this line, on this curve, y equals x to the 4th minus 6x squared plus 4, all the points where the tangent line is horizontal. So what I want to do is find the derivative, which is pretty straightforward. It's going to be 4x to the 3rd minus, what do we have? We have 12x, and that's going to be the slope. That's going to be the slope of the tangent line for any value x. Now, when is the slope 0? Well, set y prime equal to 0 and solve it. Well, you can see you can factor out an x, and you got 4x squared minus 12. In fact, I want to factor out that 4 as well. 4x times x squared minus 3. And so what we have, that's 4x, and we have x minus root 3 times x plus root 3. That means when x equals 0, or x is plus or minus root 3, the slope of the tangent is 0. Let's take a look at the graph and see if that's the case. Indeed, if you look at these points, this is exactly what you see. You have these 3 points where the curve kind of turns a corner or turns around, right? And at that moment, the tangent line would be horizontal. All right, let's look at the derivative of the basic trigonometric functions sine of x and cosine of x. So we have this theorem that says the derivative of the sine of x is the cosine, but the derivative of the cosine is the negative sine. And let's try to work this out using just basically the sum rule for the sines. So the derivative d over dx of the sine of x is going to be the limit as h goes to 0 of the sine of x plus h minus the sine of x all over h. Now let's use the fact, what is the sum, the angle sum rule for sines? That's the limit as h goes to 0 of sine of x, so the sine of x cosine of h plus the cosine of x sine of h minus sine of x, all over h. Now, what we're going to do is figure out where, well, here's what's going to be interesting for us, so what I'm going to do is I'm going to do some factoring. I'm going to split it into two limits. The limit as h goes to 0. The first one is going to be, the sine of x is as a common factor. So we'll have the cosine of h minus 1 over h, and then plus the limit as h goes to 0 of the cosine of x times the sine of x sine of h over h. Okay, so where this is the part that went over here, and these two parts went over there. Now sine of x you can be factored out because there's no h involved. So this is the sine of x times the limit as h goes to 0 of the cosine of h minus 1 over h plus the cosine of x times the limit as h goes to 0 of sine of h over h. We actually evaluated these limits earlier on. This limit here, the cosine, we talked about it with, I think, theta, but it's still the same thing. This is equal to 0. And this limit over here can be evaluated. That limit is equal to 1. That probably looks a little more familiar, the sine of h over h. So what you get is just the cosine of x. That's the derivative of the sine of x. Now, can you get this? We can actually, once this first one's established, you could actually get the derivative of the cosine of x by doing a change of variables. If you just like shift x over by pi over 4, then you turn the sine into a cosine. But so the second derivative is pretty straightforward to get in a couple of different ways once you've established the derivative of the sine. I'm not going to do it here. You can look it up if you want. So take, for example, y equals 3 sine theta plus 4 cosine theta. Well, y prime is going to be 3, the derivative of cosine, the derivative of sine is cosine, and then plus 4 times the derivative of the cosine, which is a negative sine of theta. So this is actually going to be 3 cos theta minus 4 sine theta. And that's the derivative. One thing that I like to do is to think about it like this. You have sine, cos, negative sine, and negative cos. It's kind of like a unit circle. And so for derivatives, you kind of have this pattern where you go clockwise around this circle. The derivative of the sine is a cosine. The derivative of the cosine is a negative sine. The derivative of the negative sine is negative cosine. The derivative of negative cosine would be positive sine. And remembering this picture in my mind helps me keep straight what's negative and what isn't. So that might be helpful for you. I hope it is. So as an application of this, though, it's the 27th derivative of cosine of x. So if we were to write this, let's say y equals, let's actually write, if f of x equals cosine of x, right? We're trying to find f to the 24th of x, or I'm sorry, 27th of x. Well, okay, we can one thing we can do is realize that every time you can actually write the derivative in kind of blocks, sort of. Like if you realize the cosine of x, the fourth derivative, right? The fourth derivative is actually cosine of x again. So every time you do it 4 derivatives, you're back at cosine of x. If you take the 24th derivative over so if you take the 24th derivative and then you take the third derivative of that, you're going to get the 27th derivative. This is a good way of thinking about it. Like you just add the derivatives, right? But the key thing here is the 24th derivative of cosine of x is cosine of x, because 24 is divisible by 4. So what this is the third derivative of the cosine of x. So this is going to be, if you have the sine, the cosine, negative sine, and negative cosine. So the first derivative would be the sine, the second derivative would be the negative cosine, and then the third derivative would be the sine. So this is the sine of x. Let's take a look at this example. Let's say a particle is moving around, and at any given time t, its position is going to be given by f of t. So t cubed minus 6t squared plus 9t. So we can say some things about its position and velocity. For example, the velocity at time t, we could write v of t, and that's going to be the first derivative. So for this one, it would be, if we find the velocity, it's going to be 3t squared minus what? My derivative of minus 6t squared, that'll be a minus a 12t plus a 9. So that's the velocity function for any given time t. Its velocity is given by that. So we could say, so the velocity at 2 seconds is going to be, what, 3 times 2 squared minus 12 times 2 plus 9, which comes out to be what? 3 times 4 is 12 minus 24 plus 9. This comes out to be, it would be negative 3. So at that moment, it's going to be negative 3 meters per second. It's going to be kind of going backwards at 3 meters per second. The velocity at time 4 would be 3 times 4 squared minus 12 times 4 plus 9, right? So that's going to be 3 times 16. 3 times 16 is going to be 48 minus 12 times 4 is another 48 plus 9, and so that's going to be 9 meters per second at time 4. When is it at rest? So when the velocity is equal to 0, this object will be at rest. So that's going to happen exactly when 0 equals 3t squared minus 12t plus 9. I'm going to divide everything by 3. That's the same as when 0 equals t squared minus 4t plus 3. That factors out to be t minus 1 and t minus 3. So it's at 1 second and at 3 seconds. Those are the 2 times at which this particle is completely at rest. If you want to know when this particle is moving forward, that's when the velocity is greater than 0. And so you can see that if you take a look at the if you take a look at the velocity function, the velocity function is a parabola that's opening upwards, and so since we know it's equal, the velocity equals 0 at time equals 1 and 3, the velocity function kind of looks like this. It's intersecting at 1 and 3, so 0 is over here. When the velocity is positive, that means this thing is moving forward. And so it's moving forward from 0 to 1 and from 3 to infinity. So we can say during the first second and from 3 seconds. So during the first second and from 3 seconds onward, the particle is moving forward. It kind of backtracks for 2 seconds and then it turns around and goes forward again. So if we wanted to know the total distance traveled during the first 5 seconds, what we need to do is figure out from 0 to 1 second, how far does it travel? From 1 to 3, how far does it travel backwards? And then from 3 to 5, we need to figure that out. And so what we would do is we would figure out what's f of 1 minus f of 0. That's the total distance. Now, in fact, we can just, for all of these, we can just write it as absolute values. Plus f of 3 minus f of 1 plus f of 5 minus f of 3. So if you work these out, I'm not going to do it out all here, but you can work these out all together. This is 28 meters that's traveled, this particle travels in total during the first 5 seconds. That's not the net distance, that's the total distance, meaning counting going back and forth. If you want to find the acceleration of this particle, that's going to be the second derivative. And we can find that. We can write that as like a of t, I should say. We're not using x, we're using t. So f double prime of t. So if you take the derivative of the velocity, we're going to get 6t minus 12, right? That's the derivative of the velocity. And so, for example, the acceleration at time 4 is going to be 6 times 4 minus 12. So this is 24 minus 12. That's 12 meters per second squared. That's how fast this is accelerating at 4 seconds. Okay, so let's consider an economic problem where you have a cost function. When you're producing x units, the cost is going to be 10,000 plus 5x plus 0.01x squared. So we might want to know what is the marginal cost so the marginal cost is how much each additional unit is at a given time. So if you're producing 700, the marginal cost is like how much would the 701st unit be? But it's actually the derivative. So the marginal cost is the derivative of the cost function. So you can use that to find what's the marginal cost when you're producing some number of units. For example, we could find the marginal cost at the time when we're producing 500 units. So first we want to find the marginal cost function. It's just c prime, the derivative. Okay, so the derivative of the first term, which is constant, is 0, and then the derivative of the second term, 5x, is going to be 5, and the derivative of the next term is going to be 2 times 0.01x. So this is actually 5 plus 0.02x. Okay, and so the marginal cost when producing 500 is going to be 5 plus 0.02 times 500, which is going to be 5 plus, you work that out, 500 times 0.02 is going to be 10, or $15 in this case. This is like the instantaneous, like the moment you are increasing from 500 to 501, in that moment, that 501st one is going to be costing $15 more. In fact, you can calculate the difference the cost at 501 minus the cost at 500, if you work those out, it actually comes out to be a little bit different. It comes out to be $15.01 when rounded off. It's off by a little bit because of all of these decimals, but it's not to say that the full cost of the next one. It's the instantaneous cost per item is $15. That's what the marginal cost is, which is just the derivative. So it's anyway. So I mean, that's all we're going to cover for now. We've covered derivatives of polynomials and sines and cosines, and from that we can actually build up a lot, because you can add and multiply by constants and build other functions. We interpret the derivative as a velocity if it's something physical. So we have a couple interpretations of a derivative already now. All right, well, that's everything for this section, and we'll do some more practice in class. Bye.